Hey everyone, it's Jason Allen, the concrete pipe guy and technical resource engineer for Oldcastle Infrastructure. So glad that you decided to join us for this webinar. Our topic is cement manufacturing, and it will be presented by Heath Hall, who is the technical resource manager for Ash Grove Cement, working out of their Utah operations office. Now, some of you may not be familiar with Oldcastle Infrastructure, so I will quickly share with you some of the solutions that we can provide. Now, I currently live in Utah, and I spend a majority of my time providing technical resources to design engineers, contractors, inspectors, mostly in the Mountain West area. Now, most people know us by our precast products, mainly reinforced concrete pipe, precast box culverts, catch basins, manholes. And while this has been our main focus for many years, we have added some very cool new product lines to help meet your needs. Now, Oldcastle recently acquired Torrent Resources, a company out of California that is the industry leader in dry well manufacturing and installation. We've also expanded our stormwater solutions to include storm capture, a total stormwater management system that uses precast sections for underground detention storage. Now, this system uses the strength of reinforced concrete to provide more area for storage, which drastically reduces the footprint compared to other underground detention systems. Now, we also have multiple stormwater treatment system options like sediment traps or hydrodynamic separators that can fit your specific needs and stormwater treatment requirements. And our newest addition in the Utah market is gasketed box culvert. Now, instead of the typical soil type mastic joints that we've been used to using, we now have the ability to manufacture gasketed box culverts to provide a watertight joint without any additional joint treatment. And this ends up saving a lot of time and money on installation. Now, as I mentioned before, our presentation today will be given by Ash Grove Cement's Technical Resource Manager, Heath Hall. Heath has been in the cement industry for over 20 years, both on the technical resource side and as a chemist, among other things. So with that, I will turn the time over to Heath.
Okay, great. Well, my name's Heath Hall. Jason kind of introduced me, but I work for Ash Grove Cement Company, and we're one of the major cement suppliers in the area. I do technical services for them. And prior to this role, I worked at the cement plant as the chief chemist, and I was in charge of quality control there. So, pretty good idea of how cement is made. And I really love concrete and cement, so I'm happy to be here and able to share this with you today. And by all means, please ask questions. I'll answer just about anything at the end. Of course, there's a lot of stuff I don't know too, so you can stump me. So this presentation is full of pictures, mostly from the Leamington cement plant in Utah. That's the one here in Utah. Leamington is between Nephi and Delta, and that's where we produce our cement. So just to be real clear right up front, I want to make sure our nomenclature is correct. So cement or concrete, when I think in groups like this, we get some pretty polarized opinions on people wanting to know exactly what we're talking about, that it's cement, not concrete. Oftentimes things are called cement that are really concrete. So all these pictures, these are things that are made of concrete. Sidewalks, roads, swimming pools, those are all concrete. Cement is an ingredient in concrete, and so we're going to talk about the cement. So it's the powdered glue that really holds concrete together. It's chemically reactive with water, and so when it's in the presence of water, it starts to grow crystals and harden, and that's what glues the concrete together. And it makes up it's a key ingredient in concrete, but it doesn't make up the vast majority of it by any means. I'd say usually you're probably between 8 and maybe as high as 15% limestone, or 8 to 15% cement in a typical yard of concrete. This kind of gives you the breakdown. You can see you're about 70% sand and gravel. So that's what we're talking about today is the cement. So how is cement made? Well, one thing to think about, one way to think about cement manufacturing is we're really taking a mountain, we're grinding it up into a fine powder, so fine that it can pass through an eye of a needle. Then we're going to heat it up. We're going to get it very, very hot, just as hot as it would be if it came out of a volcano. And then we're going to take that material, grind it down again until it can pass through the eye of a needle, and that is cement. So that's the basic process of making cement. It's very, energy intensive, but it's really a cool process, especially at the industrial scale. So here is a picture of just normal Portland cement, the powder, and this is our product. So we're going to talk about the manufacturing process. This is a picture taken of our plant that's near Leamington, kind of a bird's eye view. You can see the plant there, kind of in the lower right-hand corner of the picture. And then if you look back up behind the plant, you can see we're doing an awful lot of mining. Our plant is built on a limestone mine, and that's strategic for us. Limestone is the main ingredient in cement. It usually makes up raw limestone will make up about 80% of the mix. We need to have limestone along with some other materials because the finished cement has a calcium oxide content of around 60%. So we need a lot of limestone in our mix. The other ingredients are we need a silica source. So oftentimes we'll use a sandstone, but we also get silica from our clays, and some plants will use like a fly ash or some other material for their silica source. We also need alumina. So the alumina comes from clay or shell. Some plants will use bauxite. Be many different clay sources. Another ingredient we need is iron. So at that plant we use mostly slag, actually, from the old Geneva site, the old Geneva steel site. We'll also use mill scale, or we can use an iron ore. And then also as an ingredient to cement, you need some gypsum to provide some sulfates. These help regulate the set of the cement, and they're added at the end of the process. So those are our raw materials. All cement plants are built on quarries that can supply 2 to 3 of these materials. All the time they're on limestone quarries, and then we're often looking for 2 or 3 of the remaining constituents, either silica, alumina, or iron. So that kind of determines where the cement plants are located. There are a few examples of cement plants that aren't located on a limestone quarry. We have a plant in Seattle that's where they barge the limestone into that plant. Usually you're located on a limestone quarry. So at that location, there's a picture of our quarry. This picture is probably about 10 years old now. So kind of on the left-hand side, if you looked at it today, that mountain's been brought down quite a bit more on that side. But the quarry life at that particular location in Leamington, we think we have about 300 years of limestone, the current production capacity. So we've got plenty of limestone there to last us a long, long time, or at least to get me retired. Usually when they build a cement plant, they want to have at least 50 to 75 years of limestone available on site. If they don't have that much, they won't consider the site for a cement plant. The work really for us starts in our quarry. We have there we quarry limestone, and we take that to a crusher. We have a big crusher. It's an impact crusher, so it kind of has a hammer that swings around and throws the material against some blow bars. And when the material impacts those blow bars, it's crushed. And that crusher can handle material that's about 4 foot in diameter on down, and it will crush it down to be about the size of my fist. So maybe 4-inch diameter is kind of the material we're looking for to feed the plant. And the quarry, it'll operate, this crusher operates at, it's rated for 1,300 tons per hour of material production through that. So that's quite a bit of material, 1,250 horsepower motor. So right off the bat, we're getting started with a lot of energy consumption. From there, the material, once it's sized down to about the size of our fist, it goes on some belts, and it travels down to a pad, a raw material storage pad that has a stacker reclaimer system. What's interesting about this is the stacker moves back and forth. It will stack a little bit of Monday's production on the bottom, and then it works back and forth and stacks Tuesdays and Wednesdays and Thursdays and Fridays production kind of in layers. And then when we reclaim it, on the right-hand side, you can see kind of a triangular rake. That rake will go onto the side of the pile that we've stacked, and it will cut into that pile and pull off a section of material that represents the entire week's production. So it's stacked horizontally, but it's reclaimed vertically. And what's interesting about that is it helps us regulate our chemistry. You know, the limestone is really a natural product laid down by Mother Nature long ago, so the chemistry varies somewhat as we mine it. But using this method, we're able to really even out the chemistry. So we're feeding the plant with approximately the same chemistry of limestone throughout the week. And that's good for quality control folks. And we go through about, I don't know, 4,000 or 5,000 tons of raw material in just limestone a week out there. So we consume a lot of limestone. From there, the material will pass into our raw material storage silos. At this particular plant, we have 5 silos there that hold 5 different raw materials. We have one for limestone. We have actually 2 different shells on site. There's some shell seams between our limestone seams, and so we mine that shell for its alumina. It's relatively low in alumina and high in alkali. So we bring in an off-site shell that's higher in alumina and lower in alkali, and we'll feed both of those materials onto our belt simultaneously with limestone. We also have an iron silo, and we have a silo for our sandstone. So all of those silos will feed through wave feeders simultaneously onto a common belt, and we monitor the chemistry of that material on the belt in real time. We have a cross belt analyzer that uses radiation to analyze that material in real time, and we're able to adjust the relative rates of the wave feeders to keep our chemistry exactly where we want it to be. So those wave feeders adjust every 5 minutes to keep our chemistry on target. So it's pretty cool. From there, the material goes to a raw mill. So we have a vertical raw mill, and the material, keep in mind, is about these rocks are about the size of my fist on down. We're going to grind that material through this raw mill into a very fine powder. So we're going to get about 85% passing 200 mesh, which is a little bit finer than flour, and we can grind that down at the rate of about 200 tons per hour. So this is a very noisy, energy intensive process. You can see the raw mill here. This is the body of the raw mill. We have some tires at this level here. If you look on this other side, you can see the material comes in here in the feed inlet, and then it falls through that chute onto this round table here in the middle of the body of this mill, and that table is spinning. So as it spins, centrifugal force forces the material out towards the outside of the table, and then we have these stationary tires that are rolling on the table, and they will roll over the rocks and crush them down into fine powder. After the material passes through underneath the tires, it gets swept up in an airstream and travels up to the separator, which is kind of the purple piece in the middle there. And if it's fine enough, it will exit out the top of our raw mill as a product. If it's too coarse, it will actually fall back down onto the table and make another pass through the tires. So these tires, when I first went to work at the plant in 2010, we just had hardened steel table and hardened steel tires, and they would only last about 4 months. 3 or 4 months is about all we could get out of them, and those tires were about $30,000 a piece. Now we've changed that. We've put in some tires, and the table are both embedded with ceramic beads, which give us a lot more wear, and so we only have to replace those tires about once a year. But the cost of those tires has gone up commensurate with what we used to. So really, it's about the same amount of money, but we spent less time changing out the tires. As you can imagine, this is a very abrasive process, and so we have to take that mill down about once a week for a full day of maintenance to keep it running. From there, the material travels over to these blend silos here that you see in the lower left-hand corner of this picture of the plant. Inside these blend silos, the material is just stored. It's also blended with air, so there's a bunch of air pads on the bottom of those that blow the material around and try to mix that material to keep our chemistry just as even as we can keep it. And from there, the material is blown up to the top of this tall tower you see in the center here. So this tower is our preheater tower. At the Leamington plant, we have a 4-stage preheater tower. The more modern plants will even have a 5th stage. Some will have a 6th stage. And the taller the tower, really, the more heat you're able to reclaim out of the air before it goes out as waste. So what happens is the material gets blown up to the top of the tower, and then it falls down through the tower. We have a fire in the bottom of the tower that is heating the air in the tower, and then as the material, it's kind of a giant counter current heat exchanger. As the material falls down, the energy from the air transfers into the material and heats the material up. So also, we have our kiln here is kind of in the center here. It's kind of hiding behind things in this picture, but it's a 12-foot 6-inch diameter kiln, 175 feet long. And you'll hear that cement productions creates a lot of greenhouse gas emissions, and that's true. What's interesting is it's not all from the heat from the combustion of coal and things, but it's actually the CO2 we're releasing is CO2 that's been trapped in the limestone. So limestone is calcium carbonate, and we need to free up the calcium oxide in that limestone to react with the silicas and aluminates in our raw materials to form some calcium silica complexes. So to do that, we have to release the CO2, the carbonate that's been trapped in the rock for millennia, and so that's why we produce so much greenhouse gas, is we're actually releasing the CO2 that's been trapped in limestone. And you can see here this note that says clinker factor 0.6125. What that really means is that if we put in 4,500 pounds of raw feed, rock, we're only going to get 2,756 pounds of clinker out. So that missing roughly 40% of our product, the rock that we put in, actually goes out the stack as CO2. So that's where a lot of our greenhouse gases are come from. So that's a challenge for the industry as we look at sustainability going forward. This is a picture of kind of the Pyro process. You can see our blend silo in this little diagram here. It blows the material up to the top of this tower, and then these cyclones are just built to transfer the heat from the airstream into the material as fast as possible. So we have hot gases from our kiln. We have a calciner here that has a fire in it. Those hot gases are traveling up the tower as the cool feed is falling down the tower, and we're raising the temperature of that feed. So we call the process of removing the carbonate from the limestone calcinization, and that is almost entirely taking place in the tower here. The material's in the tower for like 30 seconds, and it starts. The material is just the same temperature as its ambient temperature. So today it's like 70 degrees or whatever. By the time it reaches this bottom of the tower, after 30 seconds, we're going to raise the temperature of that material from 70 degrees Fahrenheit to about 1800 degrees Fahrenheit over the course of about 30 seconds. So very, very quick temperature rise. From there, the material falls into the kiln, and as it travels along the kiln, we start getting some changes to the actual mineralogy of the material. So we're forming a new mineralogy that's hydraulic in the fact that it will react with water. So here's just another picture of our preheater tower. Kind of explains what's going on. You've got the hot gases going up. You've got the mill flowing down. This is just for efficient heat transfer. Once the air reaches the top of our tower, it's waste. We've wasted any remaining heat. So in our particular tower, we get that temperature down to about 700 degrees, and that's all the energy we're able to extract out of the airstream. So from there, we actually cool it down with water and and that air flows back through our mill that I showed earlier to keep it warm enough to operate. So the tower is hot enough; it's refractory lined, especially as you get deeper in the tower. The refractory is thicker and thicker to protect the steel from the extreme temperatures. This is just a shot of our kiln from the outside, so 175 feet long. From hot to cold, this kiln will actually expand about 18 inches, thermal expansion from hot to cold, or from cold to hot, I guess. So that's kind of interesting as well. The kiln is refractory lined. Got a picture of the inside of a kiln here. You can see this is an old picture. This isn't how we install the brick anymore, but you know, it's lined with brick like this on the inside to protect the steel from the extreme temperatures. We'll take the temperature inside the kiln can be about 2,750 degrees Fahrenheit, so very, very hot. This particular location in Leamington, we burn coal. We burn some gas, but the plant can't burn on gas alone. We have a plant in Oregon that can burn on gas alone. And we'll also burn tires in this kiln. So this is a picture of what the kiln looks like as the clinker is being discharged from the end of the kiln. So you can see it's very, very hot. The material temperature gets up to, like I say, about 2,700 degrees before it enters what we call the cooling zone. In the cooling zone, we cool the material off about 400 degrees, and that's enough to freeze the new mineralogy in place. So kind of sounds odd to say that you're freezing something at 2,300 degrees Fahrenheit, but that's what's going on. Next, we have just a picture of our kiln burner pipe here. Kind of interesting, just the size and scope of that. Let's see, did it advance the slide? Yeah, so just an idea of what's happening in the tower with chemistry. As you start raising the material temperature, you start driving the water that's bound in those materials out of the materials, and then once the water is gone, you start losing that the carbonate in the rocks. So the CO2 starts to come out, and that all takes place in the tower. Then once you get out of the tower, we start getting to the kiln and things start getting sticky. And that's why we need to get out of the tower, because we don't want to have our tower plug up with sticky material. So the material starts to melt. That's really what the iron and alumina are for in the mix, is to provide a flux that allows the material to melt and mix well. And as that melts, we start getting an association between the calcium and the silicates to form these new minerals. We call them A-lights and B-lights. You can see them forming here as material gets more and more sticky. Temperatures increase. Finally, the material starts clinkering, and then we've got to cool it off. So that's kind of just an idea of what's happening inside as we make these clinker nodules. From there, the material falls into our grate cooler. Here's a picture. Here's a schematic of a grate cooler, but you have your kiln up here. The material falls into the grate cooler. The material falling into the grate cooler as it enters is red hot. 2,000 plus degrees Fahrenheit. There's a bank of fans on the bottom of the cooler that blow air up through this bed of cooler to cool it down. And then the hot air actually gets sent back to our tower system to preheat more material. So we're able to recoup about 75% of the heat contained in the clinker for further use in our downstream kiln. So that's at some point we are unable to recoup that heat, and it goes out as waste. But what's interesting here is the material, as I said, spends about 30 seconds in the tower. It's going to spend about probably about 45 minutes in the kiln. As it travels down, the kiln rotates and turns, and it slowly makes its way down the kiln. Kiln turns at about, let's say, 3 RPM, and is on a pretty minor slope, maybe a 1.5% slope or so. So it spends about 45 minutes in the kiln. It's going to spend a couple hours in the clinker cooler cooling off to the point where we can handle it. So most of the time, the materials in our pyro process is actually in the process of cooling down. So by the time it reaches the end of the cooler, we've got it down to about 400 degrees, which is, you know, about the temperature that we bake a lot of stuff at. So now we're dealing with temperatures we're more comfortable with, at least temperatures we see in our real life. So here's the inside of the cooler. You can see what it looks like. It's all refractory lined. You can see these plates in the bottom with the holes in them where the air can be pushed up through. These plates just move back and forth, and as those grates move back and forth, they kind of force the material to move along. And here's a picture of the Grate Cooler with material in it, so you can see just how hot those clinker nodules are as they come out of the kiln. Really pretty cool process. So our product from there is clinker. This clinker from our Grate Cooler goes up on some belts and is taken to some silos for storage before we grind it. For whatever reason, they put this clinker outside, which was good because I was able to get a picture of piles of clinkers. You can see what clinker looks like. This clinker is usually around the size of like a marble or a sheet of marble. So that's kind of the size that we typically get. This is just a picture of some gypsum. We're going to intergrind this clinker with gypsum to form cement, and we're going to do that through a ball mill. So here's a kind of a picture of our ball mill. This thing is driven by a 6,000 horsepower motor, and it is actually, the motor is comes from a nuclear submarine that was decommissioned. So it's a really big motor. A few years ago, we had it kind of go to ground, and the winding in there melted together, and we had to take that to the nearest place we could get that rewound and then dipped in a dip tank was in Louisiana. So give you kind of an idea of the size of things that we have out there at the plant. It's sometimes hard to get the maintenance done locally. It's a very big operation. So this finish mill is 47 feet long, has a 14 foot diameter, and it's full of some mill balls. So we have these chromium hardened steel balls in there that are crushing and grinding the material, the clinker and the gypsum together. The front about third of this mill contains balls that are about 3.5 inch in diameter, and that's really where the crushing takes place. When the material is fine enough, it'll pass through a diaphragm we have in the middle there and enter the second 2/3 of the mill, where we have 1 inch size balls, and this is really where the grind in the material takes place. So that material passes through there, it's ground down into a fine powder, and then it passes out. This ball mill contains about 90 tons of 3.5 inch balls and 240 tons of 1 inch balls, and so it rotates. I think it probably rotates about 20 RPM, so it's rotating quite a bit faster than the kiln. As the material is swept out of there, it passes through a separator as well, and material that's too coarse is taken by some air slides back to the mouth of the mill for another pass through. And if it's fine enough, it's swept out as product. It goes through a cement cooler to cool it down. The interior temperature of that ball mill is around 255 degrees. So we cool that material down to probably about 170 degrees. So that our cement as it's produced is a temperature of about 170 degrees. And then that travels over on a belt to our finished silos. In those silos, we will hold the material for a couple of days as we complete testing. We do a lot of testing on the cement to make sure it meets all ASTM specifications and internal standards. So material is usually on site for, well, it depends on, in the winter when things are slow, we build inventory, and then in the summer when things are busier, we lose inventory. So In the summertime, our material is probably only on site for a week or less. But in the winter, we might have the materials probably on site for a month. So at this particular plant, we can produce about 1 million tons of cement per year. Yeah, so we produce an awful lot of cement, probably around 3,000 tons a day. Cement plants are kind of like light bulbs. You can't turn them up and make them run any faster. They're either on or off. In places like Utah, where we have seasonal construction, we have to build storage to contain what we make during our slow season, and then sell back to the market during our busy season. So that is a picture of our finished silo with the truck there loading out. I guess he's already loaded. He's just going to close his hatches, but cement goes out in these bulker trucks to the end customer. Usually these trucks will take the cement within about a 400-mile radius for direct delivery. If it's going to be further out than that, a lot of times we'll use rail to take the cement further than about 400 miles. But usually I'd say cement's pretty regional material. It's for what it is, it's pretty inexpensive. That may sound kind of odd to people, but there's not a lot of other products you can buy for 7 cents a pound. So the transportation costs add up pretty quick on top of that. So usually cement's not moved too far from home, although we do import cement from from other countries in the U.S. overseas. So that is kind of the quick and dirty on how cement is made. So I hope there's a lot of questions.
We do have a couple of other questions here. So Rick asks that he heard there was a cement shortage. So what's the cause? What causes a cement shortage? I know we were kind of talking about this a little bit earlier, Heath, you and I, but talk a little bit about why there would be a cement shortage and what is causing that.
Yeah, so there is a cement shortage right now. I think without getting too pointing the finger too much at the political system we got going on, but there's more cement in Utah than there's ever been right now. But there's more money as well. So right now I feel like there's a lot of money sloshing around in the economy, and it's trying to get soaked up by all kinds of building materials. I've been in this industry since about 2002. That's when I was first a batch man and was batching concrete. And so over the last 19 years, there's been a cement shortage for about three of those years, where there's more cement. Once in a while supply will get tight in the fall, and that tight supply will last just a couple weeks or maybe a month, and then there seems to be plenty of cement again. But this is an unusual year. Out of those 19 years I've been in the industry, this is kind of the third year we've seen this, and because it happens so infrequently, it's hard to bring more capacity online. A new kiln line and an existing plant would be about a $400 million investment. So that's one of the things that kind of causes cement shortages. Is it's very expensive to build a new cement line. If you wanted to greenfield a new cement plant, that'd probably be about $1 billion with all the regulations and permits and things you'd have to pursue. The United States can produce about 100 million tons of cement domestically. We can import another 20 million tons of cement through our deep sea ports, and after that, we kind of run out of. Excuse me, my phone's ringing. We kind of run out of capacity to import more. So this year, I think unfettered, the country would probably like to consume around 140 million tons of cement. But a lot of that's due to the financial stimulus, and once that money kind of gets soaked up, I think things will return to normal. So, and like I said, another issue is, I talked about the cement plant being kind of like a light bulb. It's on or off, right? So we really can't turn it up to make more. Likewise, if we have a recession, we can't turn it down to make less. We can turn it off, but we can't turn it down. So
That's interesting. That's really fascinating. I didn't realize that that there was so much issues in that with the politics in that. That's pretty fascinating.
yeah,
So
last year there were cement shortages that were more regional, and so there were cement shortages in California last year. Those had to do with the coronavirus. Some of the imported cement, hits the coasts. So California's coastal. So with the coronavirus, companies were afraid that we wouldn't consume as much cement as they planned on. So they cut off the imported cement, which takes months to arrive. So by the time you realize you do need it, it's hard to get it back on the road.
oh,
Another issue they had in California is they had those the power company. If you remember, a few years ago, they had some wildfires in California that were started by their electrical power distribution system,
yeah,
and so the power company basically said, okay, well, if it gets windy, we're going to shut the power off. And so last summer, they told their big customers, hey, we expect it to be windy, we're going to shut the power off. Well, the cement plants responded by saying, look, we can't take intermittent power service. Our cement plants things are so hot, it actually takes about a day to heat things up to the point where you can put your feet on, and then it takes another day and a half to cool it off enough that you can get inside and do work. So it's not a process we can easily turn on and off. So when the power companies came and said that we're going to have intermittent power supply, the cement companies decided to turn their plants off until they could count on power service. And
sure.
so cutting those plants off, some of them turned off for about a month, and that
Wow.
hurt supply in California last summer. So
Well, so I get so that's kind of an interesting point there. So anytime you have, kind of rolling blackouts or things in areas, does what would be I'm assuming you have, secondary power sources and different things, generators and that. What what would be like how long could power be out where it wouldn't really affect your manufacturing versus shutting it off completely? Like where's that threshold? Where does that go? Because it's one thing if you're going to be without power for a couple of hours and you could, fire up a backup generator or something. I don't even know if that's an option for your plants, but how,
you
how
know,
would that affect things with rolling blackouts? With, we heard not only California, but with the issues with Texas during the winter when they had those severe cold and they had some major blackouts and issues with being without power for a week or two. I'm assuming that would affect any cement manufacturing that was being done in Texas as well. But
well,
that's something I
absolutely,
thought about with that
absolutely,
light bulb analogy.
absolutely. The power plant, if we lose power, the plant shuts down. Um, if we have a power bump, the plant will shut down, and it usually takes a few hours, even with everything hot. Still, the system hot. It still takes a few hours to come back online. We had a wildfire out in Leamington this last year, and
Yeah.
that wildfire shut our plant down. We were down for several weeks with that wildfire and the ramifications from that. Um, but yeah, we do have backup power systems at the plant, but nowhere near what you would need to make the plant operate. So
Okay.
we'll have a power to allow us to load out. So our load out systems have backup generators. Our kiln system actually the kiln itself has a backup generator just to keep the kiln turning. It's so hot that if it was that hot and not turning, it would sag like a banana. Um, so we have to keep it turning, no matter what, or we'll ruin our kiln. So,
That was
so
that was kind of part of my next question. If you were to lose power in the middle of that process and flip the light switch off,
mhm.
do you lose your material or can you when it fires back up, are you able to pick up where you left off, or is it lost? You have to start over every time you lose power.
Yeah, we've got to start over. So we'll run
Yeah.
all our material out, and it hasn't finished clinkering, right? So it's still
Right.
what we consider raw. Um, so we've got to take that. We'll take it back up to our quarry, and we'll send it through the system with rock that we're crushing again, and kind of send it back through for another pass if we don't get it cooked correctly the first time through. So
you can reuse it. It's not lost. You can't just.
yeah, it's not ruined,
Okay.
but we've got to send it through the whole process again.
Very
You know,
cool.
another kind of interesting thing about the plant is just the demand charges. You know, the electrical consumption is so high. Like our finish mill, the demand charge on that is about $50,000. So if we turn our finish mill on for the month, there's a demand to the electrical system, and there we get a $50,000 bill in the mail for turning it on.
Wow. Wow.
So
That's,
our power bill at the plant is $1 million a month.
holy cow. That's amazing.
Yeah,
That's
yeah, more than I can cover for my home.
Yeah, that's pretty remarkable. Those are things you don't really think about, when you're thinking about how much to manufacture this. That's fascinating.
Yeah,
That
no,
is
it's really interesting to see the size and scale of a plant, what it takes to operate one. These plants are neat, so yeah, come out and see them. You know, our plant was built in 1980, and we've got a lot of guys out there. Most of the guys, the original guys, now retired, but
okay.
we love to have visitors, and we
Cool.
love to host you.
So have a good one. Thanks again, Heath, and we appreciate you.